through the unopened containers. And you can see a picture on the right-hand side, the top right, and that's what the system looks like. So you'll see a unit that sits on the floor with wheels, and it's coupled with a fiber optic to a handle, and that's the way that the user holds.
Perdón, pícale ahí, pícale.
The measurements are quite quick, between probably 8 seconds is about the fastest measurement, and the longest measurement we do is about 40 seconds, and it's designed to you. Okay? On the left-hand side, you should see some container types. We work a lot with brown paper sacks, with what we call FIBCs or super sacks, lots of brown amber glass, and lots of plastic containers as well. The image on the right-hand side, if you can see a picture there, that was actually a video of me measuring some liquids at Roche in Switzerland about 4 years ago.
Yes,
but the video went.
We played the video.
You do? Okay.
Yeah. They saw it. Okay, yes.
So this is an area where they really don't want to open the containers, and they don't want to take a sample because the shelf life begins to come if they open the container. So this costs very benefit measure the bottle.
Sorry, Matthew, can you repeat that? Because the signal was...
Okay. Yes, so on the video, this is a video of me at Roche in Switzerland, in Basel, about 4 years ago. And they were very interested to determine, to do ID verification of these liquids in these large Winchesters, these large amber glass bottles. The material has a shelf life, so they want to avoid opening the container to take a sample. Do that non-structurally without opening the container.
Okay.
Okay?
Yes.
Should we go to the next slide?
Yeah.
Okay, should be on the Raman for ID.
Yes, we are.
Okay, so we like to use Raman spectroscopy as an identity tool. Some people are familiar with working with FTIR systems and infrared methods, which again are very highly chemically specific. All the molecules that you study will have a vibrational fingerprint, is what we call it. Raman has an advantage in that Raman is generally faster to acquire the measurements and is easier to use. And because of these factors, it means that Raman is better suited throughput. When you make samples you would like to test, Raman can be faster overall. In particular, there are some regulatory agencies like Anvisa in Brazil and in Health Canada and some other areas where they demand 100% testing every container inside. You can see there the picture on the right-hand side. It's comparing the Raman spectrum from the mid-infrared spectrum. And in general, for Raman, we see very sharp peaks in that spectrum, that graph that's there. And those sharp peaks mean we get better chemical specificity. And across the world, we're seeing an increased requirement for 100% testing. More countries are signing up to the PICS scheme, PICS scheme, and that means that basically there's more sampling and more testing is required, which becomes a resource problem for those manufacturers. One area in particular is in the manufacture of injectable products, or might call parenterals. And in these situations, every is sampled to have the identity verified. So it again becomes a big resource problem in this case. Okay, I'm going to the next slide.
Okay. We're in the next slide. Matthew?
No, se fue. No hay. Bueno, lo que vieron anteriormente.
We'd like to speed this process up. Okay, on to slide 7 now.
Yes.
Okay, so what many people will do, many manufacturers will do and there may be something similar at Pfizer, is to have a flow-controlled sampling booth. And you can see a picture on the left-hand side of a stainless steel lined sampling booth. These are very expensive to
Whoa.
install without a flow.
Sorry. Wait.
Expensive running costs.
Yes. Can you repeat that?
Okay.
Sorry.
Yes. So many manufacturers that we're going to see will have one of these stainless steel lined sampling booths. And you can see that picture there on slide 7. These are very expensive to install, very expensive to maintain and run. They have lots of complicated clean down procedures, validated cleaning processes, which again requires lots of people and resource to clean these areas down. These are controlled environments, which is an advantage. You may take a few samples, containers in there one at a time or a few at a time, open these, sample them, weigh out the sample, seal them, sign the container, and then take the samples back to a quarantine area. And again, those after each material has been completed, then there's a very elaborate, maybe an hour or so cleaning time once that booth has been finished with. On the right hand side you can see a kind of a sampling thief that would be used, for example, sampling from a powder bag. And again, if we open this bag, there's a risk of contamination of the contents or of exposure to the operator. And again, this could be an issue. Very time consuming. You may be able to measure from, say, 50 to 100 sacks in day. So that's one person, one full day, just opening or sampling from sacks of material. So again, this has a cost to it. You're paying one person just for one day just to take samples, which is not very good use of your money. So I'm going on to slide 8 now.
Yep.
So our approach to this, to try and solve some of these problems, is a patented approach called spatially offset Raman spectroscopy. And the acronym we use for that is SORS, S-O-R-S, SORS. Okay, I'm on slide 9. And he was also able to show, almost 10 years ago, that it worked through what we call diffusely scattering containers, so things like paper sacks, for example, and other fluorescent containers. So we have the exclusive license to use this patented technology, and we use that in a few different products now. Okay, I'm on slide 10.
Yes.
Okay, you have slide. Okay, so there's another picture of the system. On the left-hand side, you can see the picture of the system. I mentioned this before. The right-hand side, you will see somebody holding the handheld part. We call this the probe head. And you'll see we've also pointed here to a barcode scanner. If you're working with barcodes, 1D and also 2D barcodes, we can use this information for the material, for the lot number or a batch number. And you can see somebody there in the bottom corner, somebody measuring from a paper sack. We press the probe head against the sample and we pull the trigger and that runs the measurement. The base unit has things like the computer. The computer is an industrial PC that can sit on your Windows Active Domain so that you can use your Pfizer login IDs to log into our system. The reports we create can then be sent to a server, a printer, or whatever else you might have. The software is CFR compliant. This box also houses things like the laser, the spectrometer, all the technical equipment we need to run this measurement through the containers. Okay, I'm on slide 11.
Okay.
So what I'm trying to show you here in a very basic way is how SORS works and how it is different to conventional Raman systems. And there are lots of Raman systems available, but all these other Raman systems are all traditional ways of doing Raman. And SORS is a very different way of doing Raman. So I'll describe it to you there. You see there's a number 1 on the picture. On the picture there it says 0 offset. So when we do SORS, we do 2 measurements. The first measurement, labeled number 1, is the conventional Raman measurement. And here we're looking really at the surface of the container. This is a standard method for doing Raman. But what that means is the signal we get back really belongs only to the container, really, and not much else. So our system automatically records this first measurement, number 1, and then automatically does the second measurement. You see that it always says number 2, and then it says the word offset. This is the offset in source, and it's the second measurement that we do. And you can see that we've moved the laser between the first position and the second position. Now, when we illuminate the sample with the laser, some of the energy from the laser goes into the container, then into the contents, and we can then generate Raman signal from inside the contents. And then some of that energy comes back out of the container in the area where we're looking for the signal. Okay? So now we have 2 signals, the 0 signal and the offset signal. The first one contains the information from the container, the paper, the glass, the plastic. The second measurement contains more information about the contents, what is inside the container. Okay, so now I'm on slide 12.
Yes.
Okay, we'll look at this in a little bit more detail with an example here. If we look on the left-hand side, we see a green box and a blue box. This is a cross-section for a sample. The green is the container, and the blue is the contents. Now, if you look at the top right-hand side, you'll see a green spectrum. This is the pure Raman signal from the container, the green spectrum. And the blue spectrum with 2 peaks, it says pure contents. This is the reference signal from the Raman signal from the contents. Okay? So if we take a measurement at position 1, conventional Raman, you will see the red spectrum here where it says container dominates. You see how the red spectrum here on the top right looks just like the green spectrum above it. Okay. So what that basically tells us is that the first scan really is only seeing the container. And a small amount of the peak from the blue peak is coming through on that spectrum there. Okay? So the container dominates the first measurement. If we look on the lower half of that slide now, you'll see number 2, move the laser to the second position. You see the laser has moved from the right to the left. Okay? And now we do offset signal. And you can see, if you compare now the picture on the bottom right, you'll see it says container suppressed. We see much more signal now, much more Raman signal that matches up with the content signal, and less of the features coming from the container. Can you see that?
Yeah.
Okay. So these 2 measurements that the system does, it's all automatic. The system does everything you need it to do. There's nothing for the user to do. You pull the trigger one time, and it does 2 measurements automatically. Okay. So I'm on slide 13 now.
Okay.
So you see that the 2 measurements we call the first one 0, purple spectrum. Okay, that contains mostly signal from the container, which happens to be a plastic, a polymer in this case. And you see the second spectrum, the right-hand spectrum with the red color. This is our second scan. And if you look carefully, you will see there's an additional peak now. Okay, so what the system does, the software will basically subtract the first spectrum from the second spectrum, and it automatically applies a scaling factor to that. Okay, so you can see down the middle, what we're left with is a blue spectrum, and we can match that with the green spectrum, which is what we told the system that we should see for this particular sample. Okay, so what that means is we're removing all of the signal from the contents. Is that clear?
Yeah.
All right. You still with me?
Yes, one moment.
Okay. How
do you determine the scale factor?
It's automatic. It's the algorithm we have. We wrote the algorithm to calculate this value.
Okay. Yeah.
Okay.